All right, so we're going to pick up from last time, taking a look at some pattern situations and sequences and series, which is what happens in this section. And problem number 3 starts out a little bit differently. It actually asks you about counterexamples. Now, we talked last time about a counterexample, what that is. What does it mean if you're asked to find a counterexample?
Something that proves it wrong.
Yeah, something that proves it wrong. That's what a counterexample is. Good description. So this right here is a mistake that students make frequently. So you see n plus 5 over 5, it becomes n plus 1. What did the student do? Yeah, they sort of like tried to cancel out the 5s, right? It's a pretty common mistake, and they remembered, of course, that 5 divided by 5 is 1. So, this it would become n plus 1. So if it asks me for a counterexample, it means it wants me to create an example that shows that this doesn't work. At least it doesn't work for all numbers. That's weird. Okay, so somebody give me an example. What could you use that would show that this doesn't work? And just as an FYI, most things you use are going to show this doesn't work. So what would you like to let n be to test? 100. Okay, we can try for 100. 100 is nice because it's going to make things divide nicely by 5, so I like that one. So Hannah, we're going to put this 100 in right here, right? So the n becomes 100, so I have 100 plus 5 over 5. Now I'm not trying to put it into the right-hand side. Okay, we're just doing the two sides separately. So I'm testing the left-hand side, which would then be 100 plus 5 over 5. So what is 100 plus 5? 105. And what is that divided by 5? Somebody said it, 21. So far so good? Now if I put that same value into the right-hand side, so I'm sort of testing whether or not I should put an equals between these is the idea. I would put in 100 plus 1, and what is 100 plus 1? 101, and what do you think? 101 equal to 21? No. And this is what a counterexample would look like. It's simply showing that some number that you picked, and to be honest, almost any number we pick on this one's going to do it. There is one number that won't. What number would be a not good choice here? 0. If you picked n equal to 0, it would work. So kind of as a default, choosing 0 or 1 often ends up being the one that does work. If you try something else, it'll often not. So this would be a counterexample that shows that this reasoning, if the student came to you and said, but I'm allowed to cancel things out, and you say, yes, do you remember when? When are you allowed to do this sort of an idea of canceling things out like this? Do you remember, Hannah?
It would be like 100 times 5.
So if you had, for instance, 5 times n or n times 5 divided by 5. It's when it's multiplied, right? It's when there's multiplication involved. And if there had been multiplication involved, we could have done that. But because of the addition, it doesn't work that way. So you could tell that to the student, but that wouldn't mean a lot. But if you show them an example where it doesn't work, they kind of have to believe you, right? I mean, like you gave them an example and showed that that does not work. And that's the idea behind a counterexample. All right, the next part in this section is talking about figurate numbers. And this is a lot of fun. So a figurate number is a sequence that's based on geometric patterns. It can create a geometric sequence or an arithmetic sequence. And the dots are arranged in the shape of geometric figures. So I'm going to show you the triangular numbers first. Let me try this. All right, so triangular numbers, the first thing I'm going to do is I'm going to start with 1 dot. And then I'm going to create 3 dots in the shape of a triangle. Okay? The next figure that you're going to take a look at looks like this. And I'm going to do one more and ask you to create the next one. Okay, so my symmetry is a little bit off, but you can imagine what that's supposed to look like, right? So I'm not counting anything yet. I'm just putting dots on the screen. What would the next one in the sequence look like? If this is my sequence, okay, you guys do this with the young ones, right? Do sequences that look like this. What would the next term in the sequence be? What will come next? 5 on the dot on the bottom, and then 4, 3, 2, and 1. So it would look like, we'll change colors, this. Again, it's not perfectly symmetric, but you have the right idea, right? Okay, so what I want us to take a look at then is take a look at the number of dots. So if you take a look at the number of dots, this is 1 dot, and then 3 dots. There are 6 dots, 10 dots, and 15 dots. Okay, so that's just counting your number of dots in this sequence. And, okay, I can't turn a page. Triangles aren't the only thing we can do this with. Now, if you take a look at this to decide is it arithmetic or geometric, just for the moment, let's take a look. Can you tell? How do you get from 1 to 3 if you're trying to use an arithmetic operation? You'd add 2, but then how do you get from 3 to 6? Add 3. How do you get from 6 to 10? Okay, so it isn't geometric, but do you see a pattern? Yeah. In fact, I want to show you something very interesting here that you're going to see happen in your book. So 1 to 3 is you add 2. This one you add 3. All right. Can't write small enough. 6 to 10 you add 4, and 10 to 15 you add 5. Now, you could continue this sequence pretty quickly because you see what's happening, right? The next one you're going to do is you're going to add 6. And visually, why are you doing that? Because you're adding another row on bottom that's going to have 6 dots, right? I mean, that's what's going on here. But notice what happens down here. How do you get from 2 to 3? How do you get from 3 to 4? And how do you get from 4 to 5? You add 1. So the first sequence is not arithmetic, right? And what you did right here, this process right here where you're looking to see what I add, this actually has a name. I don't know that your book calls it this. It might. But this is actually called first differences. It just means if you do the subtraction, what are the differences the first time? And if you do it the second time, what do you suppose it's called? They're called second differences. And when you did it the second time, you found out that the second differences were a constant. They were all the same. So the first differences, that sequence that became 2, 3, 4, 5, that actually was arithmetic, wasn't it? Now there's going to be a sequence that you're going to work with in your homework where they're going to do a sequence that is not arithmetic. And you're going to do first differences and you're going to see, okay, I can't do the add the same number every time. But if you do the second differences, or the third differences, or if you keep going down in this processing of doing these differences, a pattern will come apart. I mean, you'll see a pattern come about, okay? So keep that in mind, this idea of doing the differences again a second time to see a pattern. All right, let me show you another type of different figure number. We're going to do square numbers. So with square numbers, we're going to have a single dot, and then I'm going to have those 4 dots. And then I'm going to have these dots. Okay, I think I need to hold the iPad differently so that my dots don't slant. Let's try again. I want to do one more. My dots are going out of control. You know what the images are, right? They're squares, aren't they? Hence square numbers. And if we count the dots, the first set of dots is 1. The second one is 4. The third is 9, and the last one's 16. What would the next picture look like? Just the picture part. So you're working with the really young ones today, and they're doing these dots, and you're not talking about counting anything. What's the next picture? Yeah, it's 5 dots down and 5 up, right? So we would have a picture that would look something like this. Your picture is going to be infinitely better than mine because mine are just going all out of control. It should look like a square, not a rectangle. Anyway, or more square-ish. And we can talk about this sequence, right? This is 1, 4, 9, 16. And what would be the next term in the sequence? 25. And if you take a look at this sequence, it's not arithmetic, right? If I try to go from 1 to 4, I add. 4 to 9, I add. 9 to 16, I add. And 16 to 25, I add. 5, right? Or what was it? 9, right? I'm already thinking about the next thing I want to talk about. So there's two things you can do. Let me show you the same idea of what we just did on the previous slide. So this is 3, 5, 7, 9, right? That's the first differences. It's not arithmetic. But if you were to do the second differences, what do you find? They're plus 2 every time. So the second differences actually give you that pattern that you would maybe want to see. However, there's two ways then that you can think about this. So one of them is this way that we do the second differences. The other way is, do you know a way to write this it's not arithmetic, it's not geometric either. The multiplying by a number is not going to work either. So those are the only two ways that we've talked about having a constant way to actually write the term, the general term. This one actually works as well. It's pretty clear to see. What would I have to let my general term be? Remember the way we did general terms is we let n equal the term number that we were on. What would have to happen to n so it would tell me how many dots I have instead? Squared. Yeah? This would actually be the general term, my general term for this one is n squared. So for this one, you actually could create a general term. In general, I'm not going to ask you to create general terms when we're not doing geometric or arithmetic. But on this one, it's pretty clear that that's what's happening, right? You can add those and you can see, oh, I see square numbers. That is numbers that are squared. It's not by accident it's called that. But they actually come across here. Now I want to show you one thing that is an interesting, this really happened 2 falls ago. In the fall of 2011, the newly formed Hurley College of Science and Math, that's the college that I'm a part of as part of the university, had a meeting. And on the board, the value 3.1415 ... was placed, and we were asked to find the next terms in the sequence of numbers. So without talking to anybody around you, I want you to look at that and to answer the question. What would you say are the next two numbers in the sequence? Without answering out loud, Morgan, write it down. What do you think the next two numbers in the sequence should be? So everybody write something down. Okay, what do you think?
1/6.
Okay, 1/6, or then 1 and then 6 would be the next two terms. Does everybody think 1/6? What did you think, Nicole?
Well, I already know it. It's 9/2, right?
So why did you think it was 9/2 when everybody else said 1/6?
Because I memorized it in high school.
What did you memorize?
The sequence of numbers.
What is the sequence of numbers that you're remembering?
What do you mean? Just like,
Somebody said it.
oh, pi.
Pi.
Yeah, okay.
You recognize this as a different sequence, right? Everybody else was looking at it from a patterns perspective, which makes sense anyway for most of you to do, because that's what we've been looking at for the last 2 days in class, right? To see and say, oh, there's a pattern. The next two in the sequence would be 1/6. That seems reasonable. But I'll tell you, when I looked at it walking in to that particular sequence, or that particular meeting, I did the same thing Nicole did, because I hadn't been inundated with patterns by my teacher for 2 days like you guys have. I looked at it and I said, well, that's just an expression for pi. It's the first 4 figures of pi, and the next two are 9/2. So the reason I bring this up is because I want you to understand that what all of you were doing on this problem was what was called inductive reasoning, right? Remember that from last time? It was taking a specific example and trying to create something general from it. And there is room for error when we do that, because you come at it from a different perspective, and you may legitimately have the next two terms in the sequence that I was thinking of or that someone else was thinking of, but they don't match. So inductive reasoning doesn't always work. That's my point. So the ones you see are not going to have this sort of a flavor to it, but it is something to be aware of, is that there are failures in this sort of an idea, okay?